Dear students, today let us study about the extension of valence bond theory, that is hybridization. Valence bond theory is useful in explaining the diatomic molecules wherein the orbitals overlaps to form a linear molecule. When a compound is having more than two atoms in a molecule, how this overlapping takes place and what would be the geometry of those molecules? To explain this, the valence bond theory is extended with the concept of hybridization. So today let us study about what is this hybridization means. Valency of an element is equal to the number of half-filled orbitals present in the valence shell. Electronic configuration of carbon is 1s2, 2s2, 2p2, which shows two half-filled orbitals. That means that one electron is present in 2px orbital and another electron is present in a 2py orbital, and the valence shell contains two electrons in the 2s orbital. This electronic configuration shows that valency of the carbon must be 2. But in all its compounds, valency of carbon is 4. This can be explained as follows. When other elements like hydrogen, oxygen, etc. approaches the carbon atom gets excited and the amount of energy released is used to unpair and promote one of the 2s electron to the vacant 2pz orbital. The configuration of the excited carbon atom is 1s2, 2s1, 2px1, 2py1 and 2pz1. This shows that in the valence shell of carbon, it contains 4 unpaired electrons which are responsible to form 4 covalent bonds. Thus, there are 4 unpaired electrons which are responsible to form 4 covalent bonds. This explains the tetravalency of carbon. If carbon uses the 4 half-filled orbitals in the excited state to bond with 4 hydrogen atoms to form methane, then 3 CH bonds should be of one type because these are formed by sp overlapping, and 1 CH bond be of different type because it is formed by ss overlapping. As a result, in methane, one bond should be shorter because of ss overlapping and 3 bonds should be longer because of sp overlapping. But experimental results shows that in methane, all the 4 CH bonds are identical with the same bond length. To explain such situations, a new concept called hybridization was introduced. According to this concept, the valence orbitals of the atom intermix to give rise to another set of equivalent orbitals before the formation of bonds. These orbitals are called hybrid orbitals and the phenomenon is called hybridization. Hybridization is defined like this. The phenomenon of intermixing of atomic orbitals of slightly differing energies and different shapes, giving a new set of orbitals having the equivalent energies and identical shapes is called hybridization. Let us study what are the conditions for hybridization. The conditions for hybridization are as follows. Atomic orbitals undergo hybridization only when their energy difference is small. Among the combining atomic orbitals, at least one should have different shape, and combining atomic orbitals should belong to same valence shell. Coming to the silent features of hybridization. Number 1, the orbitals taking part in hybridization should have comparable energy. 2, after hybridization, the orbitals will have the same energy and identical shape. Third one, the number of hybrid orbitals formed is equal to the number of atomic orbitals taking part in hybridization. The fourth, both the half-filled and completely filled orbitals of valence shell participate in hybridization. Lastly, the hybrid orbitals are directed in space to have minimum repulsion among them, which leads to the definite geometry to the molecule. Based on this, let us study what are the types of hybridization. If hybridization is formed by mixing of s and p orbitals, it leads to sp3 hybridization, sp2 hybridization, and sp hybridization. If hybridization is involved in the mixing of s, p and d orbitals, then it results dsp2 hybridization, dsp3 hybridization or sp3d hybridization, d2sp3 or sp3d2 hybridization. The meaning of this, writing d first and writing d afterwards, is in case of a d orbital, 3d orbital and 4s orbitals, their energy difference is very less. In such cases, 3d orbital mixes with 4s and 4p orbitals. It results dsp2 or dsp3 or d2sp3 hybridization. In some of the molecules, the outer d orbital, that is the 4s, 4p and 4d orbitals, or 3s, 3p and 3d orbitals are involved in the hybridization. In such cases, the outer d orbital is involved. This results sp3d or sp3d2 hybridization. Let us study in detail about the every hybridization. Coming to the first one, sp3 hybridization. The mixing of 1s and 3p orbitals belonging to the same shell of an atom to form 4 new orbitals of equivalent energy and similar shape is known as sp3 hybridization. The 4 new sp3 hybridized orbitals orient in space at an angle of 109°28' to have minimum repulsion between them, leading to tetrahedral geometry. Each sp3 hybridized orbital has one big lobe and another small lobe, which possesses 25% S character and 75% P character. Example: methane, silicon tetrachloride, etc. Let us study the structure of silicon tetrachloride. In silicon tetrachloride, silicon is the central atom whose atomic number is 14 and electronic configuration 1s2, 2s2, 2p6, 3s2, 3p2. This electronic configuration shows that silicon atom contains 4 electrons in the valence shell. Out of the 4, the 2 are in 3s2 and 2 are in 3p orbitals. When chlorine atom comes nearer to silicon atom, the silicon atom gets excited and one of the 3s electron shifts to 3pz, which results 4 unpaired electrons in each 3s, 3px, 3py and 3pz orbitals. Before the formation of silicon tetrachloride, these orbitals of silicon undergo mixing to form 4 sp3 hybridized orbitals of similar shape and equivalent energy, which orient in space to form tetrahedral geometry with a bond angle 109 degree 28 minutes. Chlorine atom contains 1 unpaired electron in 3pz orbital. This overlaps axially with sp3 hybridized orbitals of silicon to form silicon tetrachloride. Coming to the next one, sp2 hybridization. The mixing of 1s and 2p orbitals belonging to the same shell of an atom to form 3 new orbitals of similar shape and equivalent energy is known as sp2 hybridization. The 3 new sp2 hybridized orbitals orient in space at an angle of 120 degree to have minimum repulsion between them, leading to trigonal geometry. Each hybridized orbital has one big lobe and another small lobe which possesses 33.3% S character and 66.6% P character. Example for this is boron trifluoride, ethene, etc. Let us study the structure of boron trifluoride. In boron trifluoride, boron is the central atom whose atomic number is 5 and electronic configuration is 1s2, 2s2, 2p1. This shows that the boron atom contains 1 unpaired electron in the 2p orbital. But to form boron trifluoride, it needs 3 unpaired electrons. To explain this, it is suggested that when fluorine atom comes nearer to boron atom gets excited and one of the electron in 2s orbital shifts to 2py orbital, which results 3 unpaired electrons in each 2s, 2px and 2py orbitals. Before the formation of boron trifluoride, these orbitals of boron undergo mixing to form 3 sp2 hybridized orbitals of similar shape and equivalent energy, which orient in space to form trigonal geometry with a bond angle 120 degree. Fluorine atom contains 1 unpaired electron in 2pz orbital. This overlaps axially with sp2 hybridized orbitals of boron to form covalent bond. The structure of the boron trifluoride is shown, whose bond angle is 120 degree and the geometry is trigonal planar. Coming to the third one, sp hybridization. The mixing of 1s and 1p orbitals belonging to the same shell of an atom to form two new orbitals of similar shape and equivalent energy is known as sp hybridization. The two new sp hybridized orbitals orient in space at an angle of 180 degree to have minimum repulsion between them, leading to linear geometry. Each hybridized orbital has one big lobe and another small lobe which possesses 50% s character and 50% p character. Example: beryllium fluoride, ethine, etc. Coming to the structure of beryllium fluoride. In beryllium fluoride, beryllium is the central atom whose atomic number is 4, electronic configuration 1s2 2s2, which shows that beryllium atom does not contain any unpaired electrons. But to form beryllium fluoride, it needs two unpaired electrons. To explain this, it is suggested that when fluorine atom comes nearer to beryllium atom, beryllium gets excited and one of the electron in 2s orbital shifts to 2px orbital, which results two unpaired electrons in 2s and 2px orbitals. Before the formation of beryllium fluoride, these orbitals of beryllium undergo mixing to form two sp hybridized orbitals of similar shape and equivalent energy, which orient in space to form linear geometry with a bond angle 180 degree. Fluorine atom contains one unpaired electron in 2p-Z orbital. This overlaps axially with sp hybridized orbitals of beryllium to form covalent bond. The structure of the beryllium fluoride is shown. And the bond length here, BeF bond length, BF bond length, that is boron fluoride bond length, silicon chlorine bond length. If I take, so BeF bond length is shorter and SiCl bond length is longer because of the s character in hybridized orbitals. Greater the s character in hybridized orbital, smaller the bond length. Coming to the next one, sp3d hybridization. The mixing of 1s, 3p and 1d orbitals belonging to the same shell of an atom to form 5 new orbitals of similar shape and equivalent energy is known as sp3d hybridization. The 5 new sp3d hybridized orbitals orient in space in such a way that they have minimum repulsion between them. This leads to the trigonal bipyramid geometry with two bond angles of 120 degree axially and 90 degree equatorially. Example: phosphorus pentachloride. In phosphorus pentachloride, phosphorus is the central atom whose atomic number is 15 and its electronic configuration is 1s2, 2s2, 2p6, 3s2 and 3p3. This electronic configuration shows that phosphorus atom contains 3 unpaired electrons. But to form phosphorus pentachloride, it needs 5 unpaired electrons. To explain this, it is suggested that when chlorine atom comes nearer to the phosphorus atom, phosphorus gets excited and one of the electron in 3s orbital shifts to 3d orbital, which results 5 unpaired electrons. Before the formation of PCl5, these 3s, 3p and 3d orbitals undergo mixing to form sp3d hybridized orbitals of similar shape and equivalent energy, which orient in space to form trigonal bipyramid geometry with two bond angles of 120° axially and 90° equatorially. Chlorine atom contains one unpaired electron in 3p-Z orbital. This overlaps axially with sp3d hybridized orbitals of phosphorus to form the 5 covalent bonds. The structure is shown. Next we study sp3d2 hybridization. The mixing of 1s, 3p and 2d orbitals belonging to the same shell of an atom to form 6 new orbitals of similar shape and equivalent energy is known as sp3d2 hybridization. The 6 new sp3d2 hybridized orbitals orient in space in such a way that they have minimum repulsion between them. This leads to octahedral geometry with a bond angle of 90°. Example, sulfur hexafluoride. In sulfur hexafluoride, sulfur is the central atom whose atomic number is 16 and electronic configuration 1s2, 2s2, 2p6, 3s2, 3p4. This shows that sulfur atom contains 2 unpaired electrons, but to form sulfur hexafluoride, it needs 6 unpaired electrons. To explain this, it is suggested that when fluorine atom comes nearer to sulfur atom, sulfur gets excited and one electron from 3s and another electron from 3p shifts to 3d orbitals, which results 6 unpaired electrons. Before the formation of SF6, these 3s, 3p and 3d orbitals undergo mixing to form 6 sp3d2 hybridized orbitals of similar shape and equivalent energy, which orient in space to form octahedral geometry with a bond angle 90°. Fluorine atom contains one unpaired electron in 2p-Z orbital, which overlaps axially with sp3d2 hybridized orbitals of sulfur atom to form 6 covalent bonds. Now let us study how to predict this hybridization. It's called the prediction of hybridization. Before the prediction of hybridization, so let us study the whatever we have discussed so far, the sp, sp2, sp3, sp3d2, sp3d hybridization with the way of explanation. So this slide shows about the description of sp hybridization, taking an example of beryllium fluoride or beryllium chloride. This slide shows about sp2 hybridization and sp3 hybridization. So taking an example of boron trichloride as well as a methane molecule. So this is the slide shows about sp3d hybridization. So taking phosphorus pentachloride as an example and sp3d2 hybridization, taking sulfur hexafluoride as an example. So showing the structures of these molecules. So there is one more hybridization called sp3d3 hybridization. In sp3d3 hybridization, you come across in iodine heptafluoride molecule. So this IF7 molecule is having pentagonal bipyramid geometry with a bond angle of 72° and 90°. So this hybridization is found in IF7. There is another hybridization called DsP2 hybridization. This leads to the geometry of square planar complexes. This generally we come across in coordination compounds. So the taking here as an example, tetracyanonickelate 2 ion. So all DsP2 hybridization results square planar geometries. Now this slide shows about the methane molecule, how the methane molecule is formed, and explanation of sp3 hybridization. Another example is ammonia. In ammonia, so it contains 3 unpaired electrons. By seeing the 3 unpaired electron to form a bonding in ammonia without the hybridization, the bond angle must be 90 degree. Experimental studies shows that the bond angle in ammonia is around 107 degree, which is nearer to 109 degree 28 minutes, which results sp3 hybridization. Therefore, even though a lone pair of electron, even though it contains 3 unpaired electron, so the lone pair of electron is also involved in sp3 hybridization. Because of this lone pair of electron, the bond angle is reduced from 109 degree 28 minutes to 107 degree in ammonia. Here the lone pair also should be considered as a bond. Coming to the hydronium ion. So the hydronium ion is also having the sp3 hybridization. Coming to the water molecule, so the water molecule contains the 2 unpaired electron in the oxygen. Without the hybridization, the bond angle in water must be 90 degree. But the bond angle in water is around 104.5 degree, which is close to the 109 degree 28 minutes, that is the sp3 hybridization. In water molecule, because of the 2 lone pairs of electrons, the bond angle is still reduced to up to 104.5 degree, having the greater distortion in the geometry. So like this, we have sulfur tetrafluoride molecule and its shape, chlorine trifluoride molecule and its shape, and the ICl2 minus iodine dichloride ion. So its shape is also given in this. Now, as I have told you about the prediction of the hybridization. So hybridization can be predicted using the following equation. That is, hybridization is equal to half the number of valence electrons in the valence shell of an atom plus number of monovalent atoms overlapping surrounding the atom minus charge on cation plus charge on anion. Let us take an example, boron trifluoride. Here the hybridization is half into the number of valence electrons in boron is 3. So the number of the monovalent atoms attached is also 3, and it is not having any positive or negative charge. The charge is 0. So 3 plus 3 divided by 2 will be 3, which is nothing but sp2 hybridization. Geometry will be planar. If the hybridization is 4, sp3, 3 sp2, 2 sp, 5 sp3 dehybridization, 6 sp3 d2 hybridization, 7 sp3 d3 hybridization. Let us take an ion, nitrate ion. In a nitrate ion, the central atom is nitrogen, half into the 5 number of electrons on the nitrogen is 5, and there is no attachment of monovalent atoms to the nitrogen because oxygen is divalent. So therefore 5 plus 0, and the charge on the, of course it is not at all a cation, so it is an anion, its charge is 1, so therefore it is 5 plus 0 minus 0 plus 1 divided by 2 will be 3. So nitrate ion is having sp2 hybridization. So like this, students go through all these, the various molecules and ions and their respective hybridization, how to calculate. Now these are some of the slides that shows whatever so far we have discussed in other ways. So here it is shown by a definition. What's the definition of hybridization? This slide shows about the overlapping of s and the p orbitals, resulting the hybridized orbitals where one of the lobe is bigger in size and another lobe is smaller in size. The first case, it is shown sp2 hybridization. In the second stage, it is shown sp3 hybridization. This is another slide showing sp3 hybridization, sp2 hybridization and sp hybridization. This slide shows the geometries of various hybridizations. sp gives linear geometry with bond angle 180 degree. sp2 gives a triangular geometry with bond angle 120 degree. sp3 gives tetrahedral geometry with bond angle 109 degree 28 minutes. sp3 dehybridization gives a trigonal bipyramidal geometry with bond angle 120 degree and 90 degree. And lastly, sp3 d2 hybridization results octahedral geometry with bond angle 90 degree. So this slide shows how the overlapping of atomic orbitals takes place, giving a definite geometry to the molecule. So this slide shows the shapes of the various molecules and their orbital diagrams. So beryllium chloride. So if they ask, draw the shape of the beryllium chloride, that is orbital shape of the beryllium chloride, you must able to draw the above structure. Similarly, boron trichloride, then phosphorus pentachloride, these are all the orbital diagrams. This slide shows about the structure of the ammonia and the structure of the water.